All right, class. So today we're going to be talking about photoelectron spectroscopy. And I know that we're not quite to spectroscopy. We haven't even finished molecules yet. We haven't even started molecules yet. We're on our way to molecules. But we're going to do this piece of spectroscopy a little bit early. So this is a special kind of electronic spectroscopy that's going to give us some rather useful information about atomic energy levels, or the energies of atomic orbitals. And this is going to lead us to something called term symbols and the remainder of what we have for multi-electron atoms, which is Hund's rules. And you may recall learning something about Hund's rules or hearing something about Hund's rules in Gen Chem. You may not. Either way, we're going to go through them in all their gory detail again. But to do that, we first need to know how we know we need to do that, which is going to be photoelectron spectroscopy. So what kind of information does photoelectron spectroscopy give us? Photoelectron spectroscopy is going to give us information primarily about the actual energies of electrons in orbitals, whether these are atomic or molecular. Today we're going to talk about atomic, but next week we'll be talking about molecular. And so it's also going to tell us a little bit about the ordering of orbitals, and there's much more information that photoelectron spectroscopy can give you, but what we're going to focus on today is really just the energies and ordering of atomic orbitals. So we're going to draw a really simplistic diagram. Maybe you won't think it's simplistic. We're going to try to keep it simple diagram with my not so awesome drawing skills, so it can't get that complicated, for how a photoelectron spectrometer works. So we start out where we have a light source, and this light source is providing either high energy ultraviolet or even X-ray light, depending on what orbitals we want to measure, right? So the higher energy or the deeper in to an atom or a molecule an orbital is, the more energy you're going to have to put in to ionize such an electron. So photoelectron spectroscopy is going to be based on the ionization of electrons. So we have to put in enough energy from the light to ionize the electron that we want to measure. So we're going to start with high energy, either ultraviolet, X-ray light. This is going to hit our sample, or interact with our sample, and our sample here is usually going to be a solid or a gas. You will almost never see liquids measured. It turns out that they're kind of difficult to measure because this whole process when you're measuring electrons has to be done in vacuum. And if you put a liquid in a vacuum, it doesn't stay a liquid very long, whereas solids and gases can be stably maintained within a vacuum chamber. So you have light interacting with your sample, and it's high enough energy that you can ionize an electron. So electrons are going to start popping off of your sample or popping out of your sample. And an odd, quirky fact for you today is that the angle between the light coming into the sample and the electrons coming off that we actually measure, right? Because electrons come off in all directions, but the direction that we actually measure, this angle is almost always fixed at 54.7 degrees, which in math and physics is known as a magic angle for reasons I cannot begin to explain, but it has to do with trigonometry and geometry. So 54.7 degrees, if you ever see the term magic angle, that's a magic angle. All right, so your electrons are coming off. We're measuring them at 54.7 degrees offset from where the light is interacting. And then you're going to go into this very strange shaped hemispherical time of flight analyzer. So a time of flight analyzer in general, no matter what its shape, is basically a start to finish racetrack or tube. And the electrons, we're controlling when the electrons come in with some sort of gate. So here we have this section here these are voltage gates and slits. So they're controlling the angle at which electrons come in and how fast those electrons are coming in and when they're coming in. So we're controlling that. And as they go through the time of flight, if we control when they start coming in, and we can measure how long it takes them to get to the end where the detector is, then we know that the time it takes to go across the track or go across the tube is directly proportional to how fast the electron is moving, or its velocity. And its velocity is directly proportional to its kinetic energy. So if we can measure how fast it goes through the analyzer, then we can back calculate its kinetic energy when it left the atom or the molecule. So that's the idea here. This is kind of a weird shaped time of flight. Instead of being a tube, it's two concentric hemispheres. So you have like an inner hemisphere surrounded by an outer hemisphere, and this is really three-dimensional, right? So these are sort of half spheres. Okay, so both of these spheres are charged. They have voltages applied to them to control which electrons take which path within the time of flight. So electrons with a higher kinetic energy are always going to be forced toward the outer path. They're going to be forced around near this bigger outer hemisphere based on the voltage that's applied to that hemisphere. Whereas electrons with lower kinetic energy are going to be forced to be closer to the inner hemisphere and take paths closer to that based on the voltages applied. Okay, so we're creatively applying voltages to these two metal hemispheres to control which path different electrons take. And so depending on the initial kinetic energy of the electron, by the time they get through the time of flight analyzer, they're going to be in a different position in space when they reach the detector. So we're going to use a detector that can measure space. And so our detector is usually this multi-channel array which is going to amplify the signal and cause a phosphor screen to light up as electrons come through these channels. As these channels light up or get added current in them, right, from these electrons. Electrons have current. And so you actually take photos in time of a phosphor screen lighting up. And so this is my cute little phosphor screen down here. And so you have an X and Y direction. So the X direction is this direction, right? So it's going across sort of the edge of those two hemispheres, from the outer hemisphere to the lower or the other way around, depending on how you set it up. And Y is the vertical position. So the position in X is what depends on kinetic energy. So you can see that we have three bands in the picture that I've drawn of a phosphor screen, where those are representing three different electron kinetic energies. And then what we can do with that is integrate down the Y direction to get peaks. So we can get intensity versus kinetic energy, because we can directly correlate the position in X to a kinetic energy. We don't need to know at this point how to do that. That's well beyond the scope of this class. But that is something that we can do, is directly correlate X based on the voltages applied to the original kinetic energy of the electron. So we get a graph that tells us intensity of electrons versus the kinetic energy that the electrons have. And what does the kinetic energy of an ionized electron tell us about an atom or a molecule? So I want you to think about that for a minute. In what place have we seen ionization and kinetic energy and light in this class before? Anyone remember Hertz and Einstein? Really, it was Hertz's experiment, and Einstein is the one that correctly explained it. And this is known as the photoelectric effect. So think all the way back to the very first week that we were in this class. We had light, which had an energy represented by h nu, where nu is the frequency of the light. That light interacted with a metal surface, and that metal surface had a work function of phi. And if the light had more energy than was equal to the work function, right? If it could overcome the work function, you got ionization, and electrons came off of the metal with a kinetic energy equal to h nu of the light minus the work function. How do these things connect? How does this connect to the photoelectron spectrometer we drew above? Well, work function for a metal, remember that metallic bonds are sort of like the sea of orbitals. It's the picture where all the electrons are really delocalized throughout this array of metallic atoms. But if we're thinking about individual atoms or covalently bonded molecules, we can think about work function being equivalent to orbital energy, right? Different orbitals are tied or connected to the nucleus in different ways, right? They feel that different effective charge, that different Z effective. So remember, there were these shielding effects and such that were brought up in general chemistry once upon a time, way back when, where different orbitals have different energies because they can feel the effects of the nucleus differently. And so we can think about this as being that orbital energy, because that's the energy that we have to overcome to get the electron all the way out, to get it to escape from the nucleus completely. So, all orbitals with the same n are degenerate according to the hydrogen atom, right? If we think about hydrogen atom's energy function, it only depends on n, the principal quantum number. But photoelectron spectroscopy is actually how we know this isn't true for any other atom. It's only true for hydrogen. So, if we think about hydrogen's energy, right, we have a 1s, and then we have 2s and 2p all show up at the same energy. It's at a higher energy than 1s, but it's all equivalent. There's no difference between 2s and 2p, which is hopefully not what you learned in general chemistry. Hopefully you remember that that's not true. So what we know from general chemistry and what we know actually from photoelectron spectroscopy is that the 2s is at a lower energy and the 2p is at a higher energy. And both of those are higher in energy than 1s, but they're not really degenerate. And the spacing between their energies is going to depend on which atom we're thinking about. And so, photoelectron spectroscopy is how we know this to be true, right? And it's also how we know what specifically those energies are for various atoms and eventually for various molecules.